Let's look at part 2, the production of metals, from ore to ingot. We have spent part 1 learning how to identify metals and understanding their properties. But have you ever wondered how a jagged, rusty-looking rock from deep in the ground becomes a shiny, precision-engineered gear or a sleek aluminium soda can? Welcome to part 2, the production of metals. In this section, we leave the small school workshop behind and travel to the world of massive industrial mining and giant furnaces. We are going to explore the life cycle of metal, starting from the extraction of raw ore, through the intense heat of the smelting process, and finally to the refining stages that give us the pure iron, steel, copper, and aluminium we rely on every day. Let's begin by looking at the very first step in this chain, the raw materials provided by the earth. The journey from a rock in the ground to a finished product follows a specific value chain. It starts with mining, where we extract the ore. Then comes refining and smelting, where we use heat and chemicals to separate the pure metal from the waste. Next is alloying, where we mix metals to improve their properties. Finally, the metal is formed into bars, sheets, or beams, ready for the workshop. Every step adds value and changes the metal's properties. Most metals don't exist in nature as pure chunks. Instead, they are chemically bonded to oxygen or sulfur in rocks called ores. For example, to get iron, we look for hematite. To get aluminium, we mine bauxite. And for copper, we use ores like chalcopyrite. These ores are the raw ingredients for our industrial recipes. How do we get these ores out? It depends on how deep they are. Surface mining is used when the ore is near the top. We dig giant open pits. If the ore is buried deep, we use subsurface mining, digging tunnels and shafts hundreds of meters underground. Once the rocks are out, they are crushed into smaller pieces to prepare them for the furnace. To understand modern life, you must understand the blast furnace. It is the heartbeat of the industrial world. Standing up to 30 meters tall, this massive steel tower is lined with refractory bricks that can withstand temperatures over 1,500 degrees Celsius. It is called a blast furnace because of the hot blast of air injected at the bottom. This furnace is never turned off. If it cools down, the molten metal inside would solidify and destroy the machine. It operates 24 hours a day, 7 days a week, for up to 15 years at a time. Let's look at the charge, the materials we drop in from the top. We have iron ore, the source, coke, which is coal baked into a high-carbon fuel, and limestone. As the coke burns, it creates carbon monoxide. This gas reacts with the iron ore, stripping away the oxygen, a process called reduction. Meanwhile, the limestone acts as a cleaner. It melts and bonds with the sandy impurities in the ore to form a liquid called slag. Because slag is lighter than metal, it floats on top like oil on water. We tap the slag off for use in road building, while the heavy, molten pig iron is collected at the very bottom. Pig iron is about 4% carbon, which makes it very brittle. If you hit it with a hammer, it shatters. To make steel, we must reduce that carbon to less than 1%. In the basic oxygen furnace, BOF, a lance lowers into the molten iron and blows pure oxygen at supersonic speeds. This burns off the excess carbon as gas. However, if we want to be sustainable, we use the electric arc furnace, EAF. This uses 3 massive graphite electrodes to create an arc, essentially a man-made lightning bolt, that melts 100% recycled scrap steel. This method is much faster and better for the environment. We can't just leave the steel in a giant pot. It needs to be shaped. In the past, we poured it into molds to make ingots, but today we use continuous casting. The molten steel flows from a tundish into a water-cooled copper mold. It begins to freeze on the outside while the center is still liquid. As it is pulled down by rollers, it is sprayed with water until it is completely solid. This creates a never-ending ribbon of steel that is then cut into specific lengths called billets, blooms, or slabs. While iron and steel are made through heat and chemical reduction in a furnace, our 2 most important non-ferrous metals, aluminium and copper, require much more specialized journeys. Let's start with aluminium. As we mentioned, it comes from an ore called bauxite. Because aluminium is incredibly sticky at a molecular level, meaning it holds onto oxygen atoms with massive force, simple fire isn't enough to separate them. Instead, we use the Hall-Hérold process. We dissolve the ore in a molten salt bath and pass a massive electrical current through it. This process, called electrolysis, literally pulls the liquid aluminium to the bottom of the tank. It is so energy intensive that it takes enough electricity to power a small town just to run a large aluminium plant. Now, let's look at copper. Copper is different because the ore we mine, like chalcopyrite, often contains only about 1% actual copper. To get the pure metal needed for your phone or home wiring, we use a multi-step process. Concentration: the ore is crushed and mixed with water and special oils. We blow air through it to create a froth. The copper sticks to the bubbles and floats to the top, leaving the waste rock at the bottom. Smelting: this copper froth is heated in a furnace to melt away sulfur and other impurities, creating what we call matte copper. Refining: electro-refining. For copper to be a great conductor of electricity, it must be 99.99% pure. We place the copper into a chemical bath and use electricity to move pure copper atoms from one plate to another, leaving every last impurity behind. Without this final electrical refining step, your computer's processor or your house's lights wouldn't work efficiently. While modern steel production is dominated by massive oxygen and electric furnaces, the industry still utilizes specialized equipment for specific needs, and we owe our modern capabilities to the historical methods that came before. Let's examine the cupola furnace and the puddling furnace to understand these different paths. The cupola furnace. This is a specialized vertical furnace primarily used in foundries. Its function is to melt down solid metals, such as pig iron and scrap, specifically for casting purposes. The process involves layering metal, coke, and flux inside the shell, which are then melted by an upward blast of air. The output is molten cast iron, ready to be poured directly into molds. The puddling furnace. Turning back the clock, we look at the puddling furnace. This is a historical, now obsolete method that was vital for converting high-carbon pig iron into low-carbon wrought iron. The process: workers manually stirred, or puddled, molten metal in a reverberatory furnace. The chemistry: this stirring exposed the carbon in the iron to the air, allowing it to burn off as carbon monoxide. The output: once the carbon was removed, pure iron was released. While we no longer puddle iron by hand, understanding these processes shows us the long-standing engineering challenge, precisely controlling carbon levels to determine the metal's final properties. We have looked at the massive machines and the intense chemistry of the refinery. Now, let's look at the result. This infographic shows us the most important rule in metallurgy: the way a metal is made determines exactly how it will behave in your hands. First, let's look at pig iron. This is the direct result of the blast furnace we saw earlier. Because it is produced in a high-carbon environment with coke, it retains a very high carbon content. This makes the metal brittle. It will snap rather than bend, but it also makes it excellent for casting. If you are making an engine block or a heavy machine base that needs to be poured into a mold, pig iron is your starting point. Next, we move to steel. Steel is born in the refinery. Whether it comes from the basic oxygen furnace or the electric arc furnace, the process is designed to remove the dirt and lower the carbon from the pig iron. The result: a material that is strong and ductile. Unlike pig iron, steel has high tensile strength and toughness, meaning it can be pulled, twisted, and stressed without breaking. This is why we use it for skyscrapers and car frames. Then we have stainless steel. This isn't just refined, it is alloyed. During the production process, we add chromium and nickel into the liquid mix. This specific process creates a microscopic shield on the surface of the metal, giving it its famous high corrosion resistance. It's the reason your kitchen forks don't rust even after being washed 1,000 times. Finally, we look at aluminium. As we learned, it is produced through the Hall-Héroult process using massive amounts of electricity. This electrolysis process results in a metal with two incredible properties: low density and natural corrosion resistance. Because it is produced this way, it is 1/3 the weight of steel, making it the perfect choice for everything from soda cans to giant airplanes. As we conclude our journey through the industrial world, this slide brings everything together into one beautiful, sustainable cycle. In modern metallurgy, we don't just make metal. We manage a balance between two main pathways: creation and reclamation. First, let's look at the path of creation. This is the primary path. It begins at the mine and moves through the blast furnace to create new iron from raw ore. That iron is then refined in the basic oxygen furnace, BOF, to become high-quality steel. This path is essential because it provides the world with fresh material to build our infrastructure from scratch. However, the second path is just as important: reclamation. This is our secondary path. and it is the heart of the circular economy. In this process, we take the steel that the world has already used, like old cars, appliances, and industrial scrap, and use it as the primary food for the electric arc furnace, EAF. Notice the difference here. The reclamation process is described as efficient, flexible, and lower in emissions. Because we aren't starting from raw rocks, we don't need as much energy, and we don't produce as much CO2. This pathway is how we ensure that the metals we mine today stay in use for hundreds of years to come. Whether we are creating new steel or reclaiming the old, both pathways are critical to our industrial capacity. As future engineers, you will work in a world that relies on this balance, building new things while ensuring nothing goes to waste. As we bring part 2 to a close, we look at this comparative guide. This is your master map of how we have made iron and steel, from the past all the way to the modern day. To be a good engineer, you need to know which furnace does which job. Let's look at the dominant modern methods first. The blast furnace. This is still the king of primary production. If we need to turn raw iron ore, coke, and limestone into pig iron, this is the furnace we use. It is the start of the entire chain. The basic oxygen furnace, BOF, once we have that molten pig iron, we move it here. By adding pure oxygen and some scrap metal, we refine it into high-strength steel. This is how the majority of the world's new steel is made today. The electric arc furnace, EAF. This is the champion of the circular economy. It skips the iron ore entirely and uses high-voltage electricity to melt down recycled scrap. It is the go-to method for specialty steels and sustainable recycling. Finally, look at our historical and obsolete methods. The Bessemer converter, the open hearth furnace, and the puddling furnace were the heroes of the Industrial Revolution. While they are no longer in common use today, they paved the way for the technology we use now. We study them to remember that engineering is always evolving to become faster, cleaner, and more efficient. And that marks the end of part 2, production of metals. You've seen how we mine it, how we smelt it, and how we recycle it. You now know where the metal on your workshop bench comes from. But we aren't done yet. A piece of steel might be the right shape, but is it the right hardness? Is it too brittle to be used as a tool? In our final section, we are going to learn how to change the personality of a solid piece of metal using nothing but heat and timing. Get ready for part 3, heat treatment of metals. I'll see you in the next video.